Nearly all the stars you can see on a clear moonless night are in hydrostatic equilibrium, that perfect balance between gravity and thermal pressure, the latter maintained against the loss of energy from the surface by the nuclear reactions in the core of the star. In the case of our Sun, 600 million tons of hydrogen is transformed to 596 million tons of helium each second, with the remaining 4 million tons of mass turning into pure energy. 4 million tons is enough to fill a coal train from New York to Philadelphia. And each second, that much mass disappears into energy. One coal train gone, 2 coal trains gone, 3 coal trains gone. Every second throughout the Sun's history. Now this process is irreversible, and eventually it must end when the core of the Sun becomes pure helium. Then change is inevitable. This is the story of stellar evolution and the rich world of atoms it creates. It carries our story back yet further in time, before the formation of the Earth, even before the formation of the matter that made the Earth, and all of those isotopes, the beryllium, the carbon, the nitrogen, the oxygen, aluminum, and argon, iodine, iridium, rubidium, and strontium, plutonium, thorium, and uranium, that has made our reconstruction of Earth's history possible. Now, when you go outside and look up at the night sky in a clear, dark place far from city lights, you see a pattern of stars. It may look like there are millions, but there are really only about 1,000 or maybe 2,000 that you can see with your naked eye. And if you come back the next night, you'll find that all of those stars are in precisely the same place, shining with precisely the same relative brightness, and if you manage to notice the subtle differences, having all the same colors. And indeed, if you come back 50 years later and look at that same patch of sky, you'll again see the identical stars in their identical locations with their identical brightnesses and identical colors. This leaves you with a misimpression of the universe, that it's a static and unchanging place. Nothing could be further from the truth. Stars are born, live out their lives, encounter a rather boring middle age, which some of us understand, and then die in a process, in fact, that's considerably better understood than the human lifetime. I can predict to a fraction of a percent when any given star will die. I can't make that prediction about humans, fortunately. Stars are in fact moving through the sky, and they're changing their brightness and their colors. They just do so on a long, long timescale. The stars are moving, but their enormous distances, the closest one being 26 trillion miles away, means that their motions are completely undetectable with the unaided eye in a whole human lifetime. Their brightnesses are determined by the energy they emit and their distances from Earth. Farther away means fainter for any given amount of energy emitted. But both of these, the distance and the brightness, change less than a fraction of a percent in a human lifetime for stars that are in equilibrium at least. Their colors are determined by their surface temperature. This is also constant as long as the star is in balance. Now, occasionally, certain stars are observed to change. Some stars have violent magnetic storms on their surfaces, like our Sun, but 1,000 times more intense, leading to giant flares that temporarily brighten the entire star. Some other stars, clearly not in equilibrium, pulsate regularly with periods ranging from days to years, changing rhythmically both their color and their brightness as they get smaller and bigger, hotter and cooler. Rarely, a new star will suddenly appear, brightening by a factor of 10 billion, going from complete undetectability, even with a large telescope, to being the brightest object in the sky. That certainly suggests instability. It's the combination of the overwhelming constancy of the vast majority of stars and the rare exceptions which suggests stars are both long-lived and evolving. Stellar lifetimes are so long that their evolutionary pattern must be inferred from studying many stars in different stages of life rather than watching a single star move through its life. Imagine an alien visiting the Earth. She only has a week to gather all the data she needs to understand changes that take place over a human lifetime. How would you even approach such a problem? Clearly, from one week to the next, you or I don't change in any noticeable way. And yet I certainly look different 50 years ago than I do today, and in another 50 years, I won't look like this at all. What the alien would do is what any good scientist would do, and that's just gather as much data as possible in the limited time that she has available. Now, it's not even obvious what data to gather, and she probably would be too shy to go up and make measurements of your waist size or hat size, but she can easily perhaps determine height, weight, and let's say hair color. Are those relevant to the evolution of humans? Well, a priori, she wouldn't know. But in making a large number of measurements on a large number of subjects, patterns might emerge. For example, once she got back in her spacecraft and was off to her next destination, she might start plotting the data, like scientists do, one quantity versus another, to see if a pattern emerges. So, perhaps on the x-axis she'd plot weight, and on the y-axis she'd plot hair color, ranging from platinum blonde to black, and maybe a few places in the East Village, blue. What does she see? The points scatter everywhere. There are very low mass people that have black hair and very high mass people that have black hair. There are very low mass people with blonde hair and high mass people with blonde hair. The points scatter randomly all over the diagram. The blue ones, well, they tend to be isolated in some skinny youth and some aging small old people. So they might be clustered a little bit, but in general, hair color versus weight doesn't reveal much of a pattern. On the other hand, replacing height on the y-axis from hair color, one would see a very interesting pattern of points emerging. There are two things to notice. First of all, there's a general correlation between weight and height. You might say, well, that's not surprising, but it's not obviously the case. The correlation does not imply causation, so the alien cannot infer that one starts in the lower left of the diagram and evolves towards the upper right. Indeed, my mother-in-law is actually shrinking, so she's evolving from the upper right to the lower left. The other thing to notice about the diagram, however, is the density of points. There are very few points at low heights and low weights, and there are very few points at very high heights and high weights. Why is that? Two different reasons. There are very few points at low weights and low heights because we don't spend very long in that state. We start growing as soon as we're born, and we quickly leave that state and move towards the middle of the diagram. There are very few points at high masses and high weights because very few of those kinds of individuals are formed. Nonetheless, the density of points throughout the diagram can tell us something about where humans, in this case, spend most of their time, because the number of subjects in each stage is proportional to the time spent in that stage. This harkens back to the museum analogy I used last time. The number of people in any room in a museum is proportional to the time that they spend in that museum. Collecting data in a playground at a school in which successive ages of students come out for recess would provide additional information about these growth patterns. You'd find a scattering of points when the first graders came out that was low and to the left on the diagram, and as successive grades came out, the points would gradually move up the diagram. This might tell you something about how humans evolve. For stars, we act just like the alien. We start by collecting lots of data: temperatures, brightnesses, radii, masses, distances, and chemical compositions for literally millions of stars. Our analogy to the schoolyard is to study star clusters. Collections of stars that are born out of a single cloud of material, so they're all born of the same stuff, at roughly the same time. Because as these clouds collapse, they fragment, and tens to hundreds to even thousands of stars can be born in an astronomically short period of time. For our most useful diagram, we plot points of one quantity versus another. And the one that emerges as revealing the most information is when we plot temperature versus luminosity, or the amount of energy a star emits, which we can infer from how bright it appears and how far away it is. This diagram is shown here and is called the Hertzsprung-Russell diagram. Russell is the same fellow who first dated the Earth using uranium at 4 billion years, and Hertzsprung is a Danish astronomer who independently discovered these same relationships. This diagram is the key to unlocking the story of stellar evolution. Again, it plots on the y-axis the luminosity or energy emitted per second in the star, and on the x-axis plots the temperature, but for historical reasons plots it backwards, with low temperatures on the right-hand side and high temperatures on the left-hand side. When this diagram was first constructed, people had no idea of its physical meaning. They were just plotting colors of stars, and plotting blue to red was just as sensible as plotting red to blue. The temperature scale ranges from 3,000 degrees for the coolest stars to over 50,000 degrees for the hottest, bluest stars, again on the left of the diagram. Over 90% of the stars with this range of temperatures have luminosities which systematically increase with temperature, ranging from less than 0.1% for the coolest stars in the lower right of the diagram to nearly 1,000,000 times the luminosity of our sun for the very hottest, bluest stars on the upper left of the diagram. We call this string of stars from lower right to upper left the main sequence because it's where most stars, more than 90%, are found. It turns out when we look at the mass along this sequence of stars, we find that it perfectly correlates with the temperature. That is, the lowest mass stars are found at the lower right. The 3,000 degree stars have masses of 0.08 times the mass of the sun, 8% of the stellar mass being the minimum amount that can ignite nuclear reactions at the center, as I mentioned last time. And going up the diagram, we come first to half solar mass stars, and then the sun, and then stars twice as massive, 10 times as massive, and ultimately, at 50,000 degrees, in the upper left, stars that are 80 times the mass of the sun, the maximum mass that a star can have and live in equilibrium. From cluster studies and from stellar models, we infer that the main sequence is also a sequence of lifetimes. Now, you might think that the most massive stars have the most fuel and would live the longest. That would be true if you failed to notice that the most massive stars also shine the brightest. They produce vastly more energy each second than the lower mass stars, and that takes more fuel. So in fact, the opposite is the case. The stars in the upper left, the 80 solar mass, 50,000 degree stars, only live for 3 million years, million with an M, which in astronomy is a very short time. Whereas the low mass stars, with a modest amount of fuel, use it even more modestly. Down at 3,000 degrees, less than 0.1% of the luminosity of the sun, and they live for hundreds of billions of years. Our sun, roughly in the middle of the diagram, with its 1 solar mass of material, uses it at a rate that will last for 10 billion years. Now, a small fraction of stars do not lie on the main sequence, and these provide a key to the various stages of evolution. The stories of a star's life can be interpreted from the sequence of locations it occupies on the HR diagram. Stars begin, as I have said, as large, cool clouds of gas. So cool means off to the right-hand side of the diagram, even below 3,000 degrees. And if they're large, they can radiate a fair amount of energy, albeit in the infrared part of the spectrum, and so they lie over here. As they begin to collapse, they shrink down, the core gets hotter, the outside gets hotter, so they move to the left in the diagram. And as they shrink, they get smaller, and as a consequence has less emitting area and emit less light, and so they fall down in the diagram. They descend, as we say, to the main sequence, and they adopt their location that's appropriate for their particular mass. As they collapse, they eventually make conditions in their core hot and dense enough to turn on the nuclear reaction. And then equilibrium is set, gravity is balanced by thermal pressure, and the star lands on the main sequence, a location it will hold for most of the rest of its lifetime, the boring middle age I referred to before. This goes on until no hydrogen is left in the core. The outflow of energy that's been produced by this continuous furnace of nuclear reactions, protons fusing with protons, deuterium fusing with protons, helium fusing with helium, to make helium-4. This energy flow will stop when hydrogen ceases to exist. And the core, having lost its source of support, the energy flowing out from these reactions, begins to collapse. In collapsing, two things happen. Same amount of material compressed into a smaller space means it gets denser, and as matter falls down, it gets hotter because gravitational energy is turned into the thermal energy of the particles running around inside the star. In compensation, it turns out, the outer parts of the star, which are not participating in these nuclear reactions, only the inner 10% have conditions where fusion can occur, The outer part, sensing this extra energy from the hotter core of the star, begins to expand and cool, sending the star in the HR diagram up because it's getting bigger and radiating more energy, and to the right because it's getting cooler. This is the realm of the so-called red giants. When the core is hot enough and dense enough, helium can be transformed into carbon, as I noted last time, by having 3 nuclei of helium simultaneously collide with each other and snap together to form the very, very stable carbon nucleus. Energy then is flowing outward again, and the star adjusts to reach a new equilibrium. The outer part is still much bigger than it was before, and the star on the outside is cooler than it was before. The helium reactions go even faster than the hydrogen reactions and therefore generate even more energy as they burn helium to carbon, but that energy is spread out over a larger surface, and therefore the temperature is lower, although the luminosity, the energy emitted each second, is higher. This red giant phase continues until the core becomes pure carbon, and then further readjustment is required. Mass, it turns out, is the key parameter of a star. It determines its location where it lives on the main sequence for most of its life. It specifies which new elements the star can make, and it predicts a star's ultimate fate. The sun will first burn hydrogen in its core. Then in a shell around its core, when the core hydrogen is exhausted, but a thin layer around it might be hot enough for fusion to occur. Then, when all the hydrogen is exhausted and the outside is expanded and the core has contracted, the temperature and density get high enough for helium to bind into carbon in the core. And then ultimately, when that's all exhausted, helium in a shell. The nuclear reacting core will shrink at that point because there's nothing to support it against gravitational collapse. And it will shrink down to the size of the Earth, 1% of the sun's current radius. The atmosphere will expand by a factor of 200 until the Earth is orbiting through its outer fringes. Not a very pleasant prospect for life or even the oceans on Earth, which will be instantly evaporated. In the final unstable phases of helium burning, where the nuclear reactions are very, very sensitive to the density and temperature available, helium will ignite in a shell around the core of the star, and that'll be a big pulse of energy, and so the star will start to expand because it's been kicked from the inside. As it expands, the density goes down, and the temperature goes down, and that's enough to shut the reactions off. So, then there's no support coming out of the center of the star, and the star starts to collapse again. But as it collapses, the temperature goes up and the density goes up, so the nuclear reactions turn on again. It reaches this unstable phase where it's turning on and turning off and turning on and turning off and turning on and turning off until the outer layers of the star get too big a kick and are puffed off and go drifting off into space. Over the course of many of these cycles, up to 40% of the sun's mass will be lost. Some of this material will be the helium and the carbon cooked up in the core of the star before its demise. Thus, this ejected material will enrich the clouds out of which new generations of stars will form, in particular seeding them with the crucial element carbon, crucial that is for life. The Earth-sized core will, when the final puff occurs, be revealed as the outer layers of gas drift off into space. It is a hot, more than 100,000 degrees, tiny, only 6,000 kilometers in radius, the size of the Earth, dead star. Where by dead I mean a star which has no means of generating energy. The only energy it radiates, the only reason we can see it at all, is because it's hot. It's, in Kelvin's model, the star formed hot, radiating away its energy. This star is called a white dwarf. It's very dense. 1 teaspoonful of this material weighs a ton. So imagine your SUV compressed so it fits in a teaspoon. But it's dead because it has no way to generate energy other than to cool off. There are billions of these stellar corpses scattered around our galaxy. Their age is easily determined by their temperature because all they do is cool. In the lifetime of our galaxy, nearly 10 billion years, the coolest ones have gotten down to about 5,000 degrees or so. So they're still visible, albeit faint because they're so tiny. And as time goes forward, they'll just cool further and further and further until they fade away as dead lumps of material, never to participate again in the cycle of life and death in stars. Now, all the stars with initial masses that are less than about 8 times the mass of our Sun end up as white dwarfs. However, those considerably more massive than the Sun, 4, 5, 6 times the mass of the Sun, can do multiple core burning cycles before they die and thus make more elements. They begin, as all stars do, by turning hydrogen into helium in the core. Then, when the core is pure helium, the equilibrium readjusts so the temperature and density are higher, and helium can fuse to make carbon. That's the end of the process for our Sun. But for these more massive stars, with lots more material overlying, squeezing on the center of the star, the next readjustment can make the density and temperature high enough that the carbon can start burning and make oxygen and neon and other elements. And then, when the whole core is turned to oxygen and neon, then it'll readjust again, get hotter and denser still, and oxygen and neon can turn into magnesium and silicon and sulfur and other elements as well. For stars less than 8 times the mass of the Sun, these cores then are made up of oxygen, magnesium, and neon in particular, 3 of the more common of the heavy elements, as well as a lot of the other lighter elements. And when their outer envelopes get puffed away, all of those new elements get distributed to interstellar space. Now, it turns out the maximum possible mass for a white dwarf is 1.4 times the mass of the Sun, 40% more massive than the Sun. So these stars that start out as nearly 8 times the mass of the Sun need to lose over 80% of their mass in these unstable dying phases before their cores can shrink to become white dwarfs. Stars that start out life with more than 8 times the mass of the Sun lead much more dramatic lives. Despite their much larger fuel supply, they use it up much faster. They're profligate, living much shorter lives, as I said before. Their much larger masses produce much higher pressures and temperatures in their cores, leading to the fusion of elements all the way from hydrogen to helium and helium to carbon to oxygen to neon, magnesium, silicon, sulfur, and all the way to element number 26, iron. Now, you'll recall from lecture 18 that iron is the most stable configuration of nuclear particles. 26 protons and 30 neutrons nestle together, attracted by the strong nuclear force in the most stable configuration that nature has devised. Thus, in the process of building up these elements, from hydrogen to helium to carbon, etc., we're moving down the binding energy curve. And each time we take a step down, just like when you're walking down the stairs, you give off energy. And so all of these processes up to iron give off energy, help hold the star up, and allow the star to shine. However, when the core turns to iron from silicon, a step that only takes a week, one of our weeks, the entire solar mass and a half of material at the center of a massive star turns from silicon to iron, it then tries to do the next logical thing. Once the core is all iron, well, the core has to collapse again, raise the temperature a little bit, raise the density a little bit, and start squeezing some of those particles together to make elements 27 and 28, cobalt and nickel. Why not? It's what the star has done successfully 26 times before. But since iron exists at the bottom of the nuclear binding energy curve, moving away from there requires energy. When you're at the bottom of a valley, to get out, you have to climb. And climbing absorbs energy rather than giving it off. And so, when the nuclear particles in the core try to add a few protons or neutrons to iron nuclei, rather than giving off energy, as this process of fusion has done in the past, all of a sudden, energy is absorbed because the iron has to move up the binding energy curve. The nuclear reactions, which throughout the whole life of the star has acted as a counterbalance to gravity, which was always trying to bring the star in, suddenly sucks energy out of the center of the star, aiding gravity, and gravity being very patient, crushes the star. The star goes from a size, roughly the size of the Earth, to something roughly the size of Manhattan. It shrinks from 6,000 kilometers in radius to 10 kilometers in radius. And it does so in half a second. That's an enormous amount of gravitational energy released in an incredibly short period of time. And a lot of energy released at one moment in time in a particular place is usually called an explosion. And that's exactly what occurs. The energy released in that final step of gravitational collapse blows the star to smithereens, spewing out all the elements number 1 to 26 that have been cooked up in the star over its lifetime into interstellar space. And because there's so much extra energy available in this enormous explosion, synthesizing all of the other elements from number 27 to number 92 and beyond. The energy of the explosion slams nuclear particles together willy-nilly, creating all the different isotopes of all the elements in the periodic table in that brief moment of stellar explosion. The synthesis of the elements is a long, slow process in the core of a star for numbers 1 through 26, but an instantaneous one for all the other elements. It's not surprising, then, that those other elements are rare, as they only occur in these relatively rare exploding stars we call supernovae. The star blows up except for this inner 1.4 solar masses of iron or so, which collapses in on itself with such a force that the electrons are driven into the protons of the nucleus. Electron plus proton, negative plus positive, turns into neutral or a neutron. The neutrons that are there stay behind, and an entire star, a ball of neutrons, is born. This is a star such as the one that may have irradiated our young solar system and given us our left-handed molecules for life. Neutron stars are the most extreme state of matter known. It is an entire star with the density of an atomic nucleus. A single teaspoonful here weighs 1 billion tons. So now imagine all the cars and trucks and SUVs on the planet compressed into the size of a sugar cube. That's what a neutron star is. The relative abundance of the 92 elements in the galaxy today are actually in accord with this model, in which stars synthesize all of the atoms heavier than helium. In fact, it's even better than that. The abundance ratios of uranium to carbon or oxygen to neon are predicted by this model of atoms being synthesized in the cores of stars up to iron and in the explosions which end the lives of massive stars for all the rest. As the late astronomer Carl Sagan was fond of saying, "We are star stuff." It is literally true. I have said more than once that you are what you eat, but all that you eat, excepting only the hydrogen atoms, was cooked for you inside a star. Understanding the lives of stars takes us another step back along our journey, identifying the origin of atomic constituents of our galaxy, the Milky Way. We do this by understanding the process of stellar nucleosynthesis, the creation of nuclei in the cores of stars. The oldest stars in our galaxy have only about 1/10,000th of the heavy elements that are present in our sun. Stars being born today are richer in such material by a factor of 2 or 3, all as a result of the steady creation of new atoms as generations of stars go by. Understanding this, however, just pushes the question of origins back one step further. Where did the original hydrogen and helium atoms come from that constituted the primordial material out of which the Milky Way was formed? To answer this question, we must move far beyond the confines of our own galaxy. And to understand how we read this truly ancient history requires forging a link between space and time. That will be our task next time.